Hi everyone, my name is Anh. I'm doing Master of Engineering at Darwin University. I have just completed my first year in here, so I have a bit of time. That's why I'm here to review all my previous subjects. If you see my video and find it is helpful, I will be very happy. In addition, if there is something not right, please let me know by adding the comment below the video. Okay, let's get started. Alright. So today I'm going to solve and draw a shear force diagram and bending moment diagram for a determinate structure. So before that, I'm gonna talk about what is a determinate structure and what is an indeterminate structure. So the structure can be called as a determinate structure when the total of reaction equal to the total of equation. So for example, if you have a roller support and a hinge support in here and the pilot somewhere in here, at the roller support you're gonna have one vertical reaction only because at the roller support it can rotate. Roller support can rotate and can move horizontally. So that's why we only have one vertical reaction. But at the hinge, we also have the vertical reaction as well as the horizontal reaction. Right? So in here we have one reaction, but at the point B we have two. Right? So the total reaction in here will be 3. Alright? The number is the number of the member. So we have one beam here, one beam, which means one member, right? So it will be equal to 3 times 1, and then it will equal 3. So reaction now equal to 3. Yeah. So we can say that the structure is determinate now. Determinate. So what is the indeterminate? Right, the structure is called as indeterminate when the number of reaction is greater than the number of equation, right? So for example, if you have a fixed support and the roller, so at the fixed support we have 3 reactions. One is a vertical reaction, one is a horizontal, and one is the moment. If the pilot here, yeah. So we have 3 reactions here and 1 here, which means R equal to 4, right? So the total reaction now is 4. It is greater than 3 multiplied by 1, right? So now the structure is indeterminate. Determinate, right? I can talk more about that on the next video if you want to. So now we will solve for a determinate structure. Alright, so as before, a roller and the hinge. Alright, so here's a pilot here. Let's make it a bit more tricky. So for example, we have a pilot, the 30-degree pilot, right? In here, and with the value of 20 kilonewton, right? 30 degree, right? Let's call it A, B. This one here is, let's go 3 meter, and this one is 1 meter, right? Okay, so how we deal with that angle, right? So if you study math, you will know about vector. Actually, this one can be rearranged as the vertical load and the horizontal load. Right, let's call it A. This one is B, right? So A 30 degree 20 kilonewton. So A equal to 10 kilonewton multiplied by sin of 30, right? So sin of 30 is 0.5, isn't it? Yep, so it's gonna be 10 kilonewton, right? So the B equal to 20 kilonewton multiplied by cos of 30 degree. Yep. So 20 cos. So it's gonna be 17 kilonewton, right? Oh, good. Now we're gonna do a very important, which is the free body diagram, which I should do before I calculate the force. So as you know, at the roller we only have one reaction, which is a vertical, so I will call it VA, right? At B also have the vertical reaction VB, a horizontal reaction as well, and this one with the value we calculated, 10 kilonewton, and then this one is 17.32 kilonewton. Now next thing we need to do is calculate the vertical reaction at A and at B. For example, if you want to calculate the vertical reaction at A, you can take the moment at B equals 0. If you want to calculate the vertical reaction at B, you can take the moment at A equals 0. So let's do it. Let's take the moment at A equals 0, right? Because as a roller support, moment equals 0, right? So the 10 kilonewton force will make the beam rotate clockwise. So we're gonna write it positive 10 kilonewton multiplied by the lever arm. The lever arm in here is 3 meter. So 3 meter. And then we have the vertical reaction at B, which make the beam rotate anti-clockwise, right? So anti-clockwise is negative. So VB multiplied by the lever arm, which is 4 meter. What else? Nothing else, because this is the axial force. The axial force doesn't make any moment, so the whole thing will be equal 0. VB equal to 10 kilonewton multiplied by 3 meter over 4 meter. Let's cancel out. And so this VB will be 7.5 kilonewton. 7.5 kilonewton here. Right. Now to calculate the VA, vertical reaction at A, you can either take the moment at B, or you can take the sigma Fy equals 0. So it can be right like this: VA VB P equals 0. So VA plus 7.5, because it's go upward, but the P is go downward, which means the negative sign. So 10 equals 0. So from here you will have VA equal to 2.5 kilonewton. 2.5 kilonewton. There's some way to do it. It's not that only one way. So with that kind of structure, which is the 2 simple support and 1 point load, the vertical reaction can be determined like this. So it can be determined by P multiplied by B over the total length, right? And so P is 10, time B is 1, L is 4, so it's end up with the same results. Same VB, same thing. L equal to 10. Now A is 3, 4, so 30 over 4 is 7.5 kilonewton. That's another way, right? Alright. And so from here you can draw a shear force diagram now. Alright, let's draw it. Let's draw the shear force diagram now. So in here you have VA with the value of 2.5 kilonewton go up. 2.5 going up, right? But between that we have nothing. We don't have force, we don't have chain, which means it remains constant until it reach the point C. Here we have the point load 10 kilonewton, push it down, so which means 2.5 minus to 10, it will be negative 7.5, so negative 7.5, right? Same thing in here, we have no change, it remains constant until it reaches the point B. It will have the vertical reaction at B is 7.5 to push it back again, back to the 0, right? Which is right. So this is our shear force diagram. Okay, now I'm gonna draw a bending moment diagram. So because of the shear force diagram, it is a straight line, so the bending moment diagram will be a linear line, something like this. So without knowing the value, I still can know the shape of the bending moment diagram. So the MC equal to, you can either use VA multiplied by the A, which means the distance here, or you can use VB multiplied by B. So 2.5 times 3, right, and this one is 7.5 times 1, will end up same thing, 7.5 kilonewton meter. So I will know that's 7.5 kilonewton meter here. There's another way to calculate it. The value of the moment will equal to the area, right? Will be the area of the shear force of this one, which means 2.5 multiplied by A, which is 3, so it will end up exactly the same thing, right? And the area here is 7.5 multiplied by 1, so it's end up exactly the same thing. Let's do an extra shear force diagram. We have the roller at A, we have hinge in here, hinge at here, and you have the axial force with the value of 17.32, right? So look at that, because of the roller, it can move horizontally to the left, either to the right. So there is no compression or tensile in this part. Do you agree with that? Because of the hinge, it cannot move horizontally, so it cannot move this side. No, cannot move. And the force will make the beam in here under the tensile, which means it is pulling the beam, right? If it's under tensile, it means it is positive. So in here, positive, with the value of 17.32, negative, right, 0. So that's your axial force diagram. Okay, that's it for today. Next video I'm going to talk about I don't know yet, but maybe second moment of area or first moment of area or something like that. Alright, see you on the next video.